My heartfelt greetings to everyone assembled here, and I sincerely hope that all of us are doing well during the advent of this pandemic. Myself, Nazeel Sabah from India, am here to discuss my paper for this conference. So let me move on to share my screen and proceed further. I hope the slides is visible to everybody. The topic of my presentation today is a comprehensive report on September 28, 2018 Indonesian tsunami. It is authored by myself, Nazeel Sabah, and my mentor, Dr. Dayashankar. We belong to Indian Institute of Technology, Roorkee. Well, tsunami is one of the deadliest natural hazards that mankind has ever experienced. If you see the historical tsunami worldwide, we can see that most of the tsunami are localized along the Pacific Ring of Fire, along the coastal countries which surround the Pacific Ocean. Basically, a tsunami is disturbance in an ocean, most probably in an ocean, where a large amount of water is displaced. And the displaced water cause huge scale devastation. If we see the number of fatalities worldwide, century-wise, we see that 21st century has killed around 2 lakh, around 250,000 people. So we have the fatalities century-wise here. Coming to the maximum magnitude tsunami obtained was 9.5 between 1900 and 2000. So all this data is between 1500 till 2018. Now coming to what fraction of earthquakes lead to tsunami century-wise, we see that in the 21st century, 231 tsunami resulted out of 1072 earthquakes worldwide. Now coming to the causes of tsunami. Predominantly, the cause of a tsunami is attributed to earthquakes, but there are other causes as well, which could be volcanic, landslide, meteorological, or a combination of all of these. So coming to the combination part, we have around 3.8% combined, caused by earthquake and landslide together. And these are some of the examples, some of the percentages of tsunami caused by combination of events. Now, coming to the study area, that is the Indonesian part, and the island of Sulawesi, which experienced a severe earthquake of around 7.5 magnitude on moment magnitude scale by USGS on 28 September. So coming to the historical tsunami of Indonesia, we see that between 1500 and 2018. So this is the chart for that, and you can see a lot of tsunami occurred in this region, up to magnitude starting from, I have listed magnitude starting from 5.4 to around 9. So this is a tsunami-genic zone and a highly active seismic zone too, obviously. Now, coming to the Indonesian islands, we see that Indonesia had experienced 2 tsunamis in 2018, one on September 28 in Palu Bay and the other on December 22nd in Krakatau. So both have a different mechanism. Palu Bay tsunami was caused because of an earthquake followed by a submarine landslide, whereas Krakatau tsunami resulted because of a volcanic eruption. Both have completely different mechanisms. Now, coming to the geographical characteristics, Indonesia is basically the largest archipelago in the world, combination of islands. It has around 15,000 islands. So different sources suggest different number of islands. So this is basically the map of Indonesia, and we are concentrating on the Sulawesi region. Well, it is the largest island country, around 18,000 island groups. It has around 5 million square kilometers of area, including both land and sea, and Sulawesi is the 11th largest archipelago in Indonesia. A reassembly of fragments was resulted, leading to the development of what is modern-day Indonesia. Now, we'll talk about the regional geology of Indonesia. So this is basically a map of the geological prevalence in Indonesia. So quaternary deposits are the predominant deposits found there. Now, coming to the Sulawesi, the island of Sulawesi, and it has around experienced 397 documented strong earthquakes and 256 documented strong tsunami till today. Now, coming to the geological features of Indonesia, it has a complex geology. Basically, the formations are metamorphic. encroached by plutonic formations and overlain by quaternary deposits. Gneiss, schists, and quartzite are the rock formations present. Western Indonesia is underlain by continental crust, whereas the eastern part has more of ophiolitic crust. The origin of Indonesian archipelago can be traced back to 300 million years ago when the Gondwana supercontinent barged into the Eurasian continent. Located around the central Indonesia, north central Indonesia. So we'll talk about the geology there, and the Sulawesi island basically steeps from the seashore to non-volcanic mountainous interior. It came into existence when fragments of crustal materials from Australian and Asian plate collided with island arcs of the Pacific. Due to a complex and multiple tectonic origin, a large number of faults crisscross the island of Sulawesi, thus making it very, very much susceptible to earthquake and tsunami. So this is basically a geological map of Sulawesi region in particular. Now coming to the seismicity and tectonic configuration of Indonesia, particularly Sulawesi. The island is where the Sulawesi was the place where the 28th September tsunami hit the west. The Sulawesi island is basically located at a very complex juncture between the Eurasian, the Philippine, the Pacific and Indo-Australian plates, and a lot of microplates have resulted because of the interaction of these major plates. The Palukoro fault is a fault that is majorly responsible for the tsunami. It demarcates two straits, and the Palukoro fault slip range between 32 to 45 mm per year. And this Palukoro fault, where the 28th September tsunami epicentered around, had witnessed a lot of earthquakes in the past, like in 1905, 1907, etc. And historical catalogs identify that 3 major earthquakes occurred in the last 2000 years, and thus making the recurrence interval of around 700. 3 major earthquakes in 2000 years and recurrence interval to be around 700 years. So this is the complex interaction of tectonic plates around Indonesia, around Indonesian archipelago. Now coming to the tsunami and earthquake history of the island of Sulawesi between 1860 and 2018. So these are the lot of earthquakes of various magnitudes that occurred that hit the island nation. The tsunami that hit between 1860 till 2018 in Sulawesi are listed in this map. Let's see what caused this particular tsunami on 28th September and what makes it of concern to us or of interest to us. Basically, the fact that this tsunami was caused by a strike slip fault called Palukoro fault is really intriguing, because most of the tsunamis are not caused by a strike slip fault, whereas most of them are caused by reverse fault. But this tsunami was caused because of an earthquake that occurred on a strike slip fault. So that is one of the most important peculiarity of this devastating tsunami. So one of the reasons why there was an amplification of seismic waves was the fact that Sulawesi is composed of rocks which are aged more than 1 million years. And they were very weak and decaying. So this was the reason behind the amplification of earthquake waves. Also, the Palu is a city in Sulawesi. It is located over thick layers of sediments. Right, because of the sediments, the amplification of seismic waves was caused, as these sediments can vigorously move vigorously and behave like a liquid. So this is the Palukoro fault, and the strike slip occurred over there. Now, what could be the reasons of a tsunami being generated? Yes, obviously it's a strike slip fault, and then a tsunami is not expected on a strike slip fault. But one of the reasons could be submarine landslides that occurred. Okay, submarine landslides in the ocean, in the Palu Bay, which could have resulted in intensified tsunami wave. Another reason could be the shape of the Palu Bay itself. The Palu Bay is a long, narrow, and funnel shape, and that was responsible for destructive tsunami waves. Earthquake itself is of high magnitude 7.5, and that was a reason of amplifying the seismic waves. Also, the earthquake was very shallow. It caused greater seabed displacement and thereby intensifying the tsunami waves. Submarine landslides are one of the most important causative factor for converting a strike-slip earthquake into a devastating tsunami. So basically, this figure explains the mechanism of submarine landslip. So because of the strike-slip faulting, because of the strike-slip earthquake, this portion under the seabed uh, got dislodged, and because of that, there was a upward force in the water body, and this led to development of a tsunami. Right. Now, coming to the foreshocks main event and aftershocks. So the main event occurred at around 6 p.m. Indonesian Standard Time, and the foreshock event started 3 hours prior to the main shock. And there were a lot of them. The largest foreshock measured around 6.1 on MW scale. And within the next 24 hours after the main shock, there were around 165 aftershocks. 14 of them had a magnitude of 5 and above. Just few days after that, around 4 days, another aftershock having a magnitude of 6 struck the island. This is a map which shows all the epicenters of the aftershocks and foreshocks. And the main shock is represented by a star. This is basically a shake map which shows the intensity of the earthquake across various parts of the Sulawesi because of the 28th September earthquake. Coming to the tsunami, the Ministry of Communication sounded a tsunami warning just 5 minutes after the main shock, and it expected time of arrival to be 20 minutes, and the wave height expected was 0.5 meter in Palu and 0.5 meter to 3 meter in the other parts. But the wave height that actually hit the island was way higher than that was predicted. It was 2 meter in Palu, and the prediction was 0.5 meters. And from the other parts, it was more than 7 meters, where the prediction said only 0.5 meter to 3 meter. And the tsunami hit 25 minutes after the main shock. So there was a reason why this Palu Bay experienced waves that was outsized as compared to the causative earthquake, and that have been already mentioned, the significant reason being submarine landslides and the shape of the bay. And the intensity of the tsunami calculated as per solar wave scale was around 2.96 according to this equation, where h is the mean tsunami height on the shore. Now coming to satellite imagery before and after the tsunami, so we can see that Palu waterfront was like this, and Palu waterfront after the tsunami looks something like this, and was a dense settlement in Tebo, and because of liquefaction damage, the entire settlements gave away. And this was an iconic Palu bridge, which is arched in shape. This bridge also suffered severe collapse. And this is a Palu jetty. This also completely destroyed because of the tsunami. Coming to human losses and damage. So around 2010 people were reportedly died on 9th of October. 10,700 injured, 5,000 missing, 70,821, around 70,000 people had to be evacuated. A lot of houses were damaged. Palu's airport was dysfunctional, where the runway developed a 500-meter long crack. A lot of ports in Palu also suffered severe damage. Guamas Harbor got shifted rightwards by 3 meters. Jumbo and Palu Bridge got completely collapsed. Major roads and telecommunication networks were also collapsed. WHO reported 2,100 deaths by 19th of October. Also, a lot of severe injuries. Also, the tsunami caused a lot of other bacterial infections as well. Coming to the soil liquefaction, a large number of buildings damaged because of this earthquake and tsunami, and one of the reasons of this damage is soil liquefaction. Like in Tebo city, a lot of important parts of the city suffered severe damage. Now, because of this violent shaking, the pore water pressure between the soil particles increases, and the soil eventually loses its strength and stiffness. That is how liquefaction impacts. So the soil behaves like a liquid. In Balarao city, 35% of the people lost their life just because of liquefaction damage. This is the liquefaction map of the area, liquefaction probability. So color coded, and this shows the areal extent of the liquefaction damage, and this shows the population exposed to liquefaction damage. Similarly, landslides was also one of the important after effects of the tsunami. Of the earthquake. important effects of the earthquake, I would say, rather. So around 1,700 homes were lost in Balrao. A lot of liquefaction and this, as well as landslide damage, were spotted in north of Palu, south of Palu as well. And this map shows a map of landslides, landslide probability color coded, and the aerial exposure to the landslide and population exposure to the landslide. And we did a Coulomb stress change study for this particular earthquake to ascertain whether the aftershocks were caused because of an increasing Coulomb stress change or not. So basically, the physics of mechanism of earthquake generation suggests that the rocks keep on accumulating stresses within them over a long period of time, and these stresses get released to the weakest part of fault planes, through the brittle crustal fault planes in particular. So because of that, an earthquake is resulted. So I took a spring mass analogy for this, and I have a crank with me, and this is the rock particles, and that is accumulating stresses. And if I keep on rotating the crank, a particular rotation, the mass will not move towards me, but after a particular number of rotations, the mass would start moving towards me. So this is something that can be related to or called as Coulomb failure stress for rocks. So where delta tau is the shear stress and mu dash is the effective frictional coefficient, and delta sigma n is the normal stress. Now, I took around 6 aftershocks of this main shock event, and I found out all the strike, dip, and rake parameters and both the focal plane solutions, and I calculated the stress change, both the shear, normal, and Coulomb stress change, using Coulomb 3.3. It's an open source software available and developed by USGS. So after this, I found this is the location of the epicenter of the next event. So, and this blue is the negative stress change, and the red is a positive stress change, or red, or I would say red part shows the stress accumulation, and the blue part shows the stress release. So we see that the epicenter of the next event in this map, in this diagram, is on the blue part. That is, it is on the part where the stress is being released. So for all the other aftershocks, I did this sort of calculations. So yeah, so I have around 12 maps like this for 6 events for both the focal plane solutions. Yeah. So what do we interpret from Coulomb stress change? So Coulomb stress change was in the range of minus 0.695 to 0.036 bar. Previous studies have suggested that even a 0.1 bar change in Coulomb stress could lead to a subsequent earthquake. So what we find here, only 2 computational results are positive, all others are negative. That means only 2 computational results suggest that the aftershock resulted because of an increasing Coulomb stress, and most of them, 83%, resulted in areas of where the stresses were already dissipated, or of areas of negative Coulomb stress change. All these conclusions suggest towards a possibility that Coulomb stress change did not contribute to the development of series of aftershocks in the Palu-Koro fault. Now, coming to the concluding part of this presentation. So there were around 2,000 people who died, 10,700 injured, 5,000 people missing, and 70,000 were evacuated. A lot of houses were reportedly damaged, telecommunication and transportation were damaged, countless number of building and public infrastructure were damaged. So the basic cause of this tsunami, of basically the intensified jolting as earthquake waves, was because of the very old rocks in Sulawesi, which led to an amplification. Also, thick sediments present in Palu area amplified. So intensification of tsunami could be because of submarine landslips and the shape of Palu Bay, which was long, narrow, and funnel shaped, which led to focusing of tsunami waves. So most of the studies suggest that the Palu Bay tsunami was basically caused by a strike slip fault rupture, which subsequently resulted in a submarine landslip in the ocean, and further resulted in vertical movement, and eventually conspiring to create a tsunami. So these are my references. I'm done with my presentation, and I look forward for any questions. Thank you so much for your valuable time.